Welcome friends. Today in the daily 5 by electrical MCQs we are going to solve from question number 474 to question number 478. Okay. So as you can see we are going to start with the question number 474. What it says? It says the energy stored in the magnetic field in a solenoid of length 30 cm and diameter 3 cm wound with 100 turns of wire and carrying a current of 10 ampere. Okay. That means you have to calculate the energy stored inside the magnetic field of that solenoid when it is carrying a current of 10 ampere. Now what you can see from the solution? First we have written what are the available quantities. Okay. L is the length of the solenoid. Then N is the number of turns. D is the diameter. And I is the current which is being carried by the wire of the solenoid. Now as nothing is given, so we have taken the core is to be of air, and here you can see what is the length and what is taken to be as the diameter and what is as the cross sectional area of the solenoid. Now we know that the inductance of a solenoid is given by L equal to mu 0 into mu r into n square into A by L. Okay, so this A is nothing but the cross section of the solenoid. Okay, so we have to calculate this area. Now what is this area? This area is nothing but pi d square by 4. Okay, now putting all the values of the given parameters, we can easily find the value of the inductance of the solenoid to be as 2.97 millihenry. Okay, now what's next? Next is we have to calculate the energy stored. Now before that, one thing I want to tell you that we know that the value of relative permeability of air is 1 and the permeability of absolute medium, or you can say the permeability of air, is taken as 4 pi into 10 to the power minus 7 Henry per meter. So these values have been used here. Okay. So next, the energy stored. The energy stored is given by half L I square. So just put the value of L and the value of I, that will give you the energy stored in the solenoid. Okay. And what we can calculate? We can calculate this value to be as 0.1487, which is approximately equal to 0.15 joule. So this will be our answer. So the option number B is the correct answer for question number 474. Next, we will go for the question number 475. It says Kirchhoff's law fails in the case of which of the following options. Now, as we know, Kirchhoff's law are of two types. One is KCL, another is KVL. KCL is Kirchhoff's current law and KVL is Kirchhoff's voltage law. Okay. The Kirchhoff's current law is based on the principle of conservation of charge, whereas the KVL is based on the law of conservation of energy. So these two laws are basically universal. That means in any kinds of circuit we can apply this law. Thus we can say that in case of non-linear as well as the linear circuit, it will be valid. But none of the options are given in such a manner. So here we will not be able to give the answer from the given options, but we must know that Kirchhoff's law is applicable for both linear and non-linear circuits. Okay. So next we will go for question number 476. Now what it says, in this question it is given that supply voltage to an induction motor is reduced by 10%. Then the maximum torque will be decreased by how much amount? Okay. So what we know? We know that the maximum torque produced in a induction motor is proportional to the square of the input voltage, isn't it? So if tau m2 is torque for the reduced voltage and tau m1 is torque for the initial voltage, then we can have the ratio of these two torques to be as V2 by V1 whole square. Now this V2 is the reduced voltage. How much is reduced? The voltage is reduced by 10% from V1. That means now the new voltage is 90% of V1. So this V2 can be written to be as this 0.9 V1 and V1 remains V1. So what we get? This is to be as 0.9 square is equal to 0.81. So we can calculate the reduction in maximum torque by tau m1 minus tau m2 by tau m1 into 100%. Now we know that this tau m2 is equal to 0.81 tau m1 from this calculation. So putting this value, what we get? We get this and we get the answer to be as 19%, which is approximately equal to our option number C, which is 20%. So option number C will be the answer for question number 476. Okay, let us do the question number 477. Okay, so what it says the derivative of an ideal step function is an impulse function, 0, sine function, undefined. As we know that unit step function is generally given by ut. So any step function can be given by a into ut, where a is the amplitude of the step function. So it is taken to be as xt. Now dx dt is the derivative of this step function will be equal to a into du dt. Now we know that the derivative of the unit step function is given by delta t, which is nothing but a unit impulse. Okay. So a into delta t will also be a impulse function. So here our answer will be the option number A, that is the impulse function. Now with respect to this question, we must also know some other things. That is what we get when we integrate a impulse function. We can see that we can get a step function by integrating a impulse and again get the impulse by taking derivative of the step. Again, with a step function, with the help of integration, we can get a ramp function, and with the help of derivative, we can get a step from the ramp again. And finally, a ramp function when integrated gives a parabolic function, and again when a parabolic function is differentiated with respect to time, we get the ramp function. Now, I think you all know about the graphical representation of this function. So this is the representation of a impulse function where at time 0 we get a response or the pulse of infinite height, and this is our step function which is a fixed value for t greater than equal to 0, and for t less than 0 the value of the function is 0, and this is a parabolic function and this is a ramp function. Okay. Now the last question, the question number 478, what is the approximate value of the surge impedance loading of a 400 kV 3-phase 50 Hz overhead single circuit transmission line? Now for a single circuit transmission line, overhead transmission line, the surge impedance is approximately equal to 400 ohm, and this information is given for underground cable because you can utilize this for any other type of problem which is having underground cable. The value of the surge impedance is 40 ohm for underground cable, whereas it is 400 ohm for a overhead transmission line. Now the surge impedance loading is given by the square of the per phase voltage of the system divided by the surge impedance, and as we have to find out the total power with respect to the surge impedance loading, so we have to multiply this with 3, and from this, as we know, the phase voltage is given by 1 by root 3 times the line voltage. So the phase voltage becomes 400 by root 3, and this 10 to the power 3 because the system voltage is 400 kV, and again as Zs is given by 400, so it is divided by 400 and multiplied by 3 as the number of phases are 3. So this calculation gives us the surge impedance loading to be as 400 megawatt for the given system. So the option B will be the answer here. Okay. Thank you all. Thanks for watching.